Well, we are at the first lecture of the series of talks, which has a rough title as singular traces in non-commutative geometry and analysis. And today we will speak about, and today and maybe the next lecture, we will speak about the singular traces and Dixmier traces itself. So today, mainly, we speak about the Dixmier traces. And to start it, before we introduce the notion of Dixmier trace as it was done by Dixmier, we need some preparations. So then the first stage of the preparation is extended limits. So definition. A linear functional omega on L infinity, and L infinity is the space of bounded real valued sequences. Real valued sequences on this set of natural numbers with the supreme norm with the uniform norm. So this linear functional is said to be an extended limit if for every convergent sequence, the value of this function will simply coincide with the limit. If the limit exists. So extended limits are just the extension of the usual limit functional from the space of convergent sequences to the space of all bounded sequences. Their existence is proved, well, can be proved, there are several ways of doing this, can be proved via Handler theorem. Which is exactly the theorem which allows you to extend a functional from a subspace to a subspace. So since the existence of extended limits is proved via the non-constructive Handler theorem, all of these guys, the extended limits, are non-constructive. So there are plenty of them, but we do not have a direct access to them, so we do not have a formula for them. But anyway, let's speak about some examples of them, and before that, we start with a simple property of extended limits. Simple property. If we take two sequences, x and y, bounded such that say x is convergent that there exists limit, well, y. Now, where is the eraser?
Right.
This one? No?
Right.
So just the limit, regardless of the value. If the limit exists, then for every we have omega of the product equals to omega of x times the limit of y. So if we have a product of two sequences and we apply the extended limit to, then the sequence which is convergent can be factored out with its limit. The proof is fairly simple using the epsilon delta terminology and the fact that every extended limit vanish on compactly supported sequences. Because compactly supported sequences, they are eventually zero, so they are convergent to zero. So every extended limit vanishes on them. Okay, that's the simple property which we will use many times.
Alex,
Yeah.
so first, the linear function is defined for convergent sequence, right? And then you extend it to the L infinity.
Yeah, so this limit functional is defined on convergent sequences.
You can regard that this linear function first is defined on let's divided by 6.
Yep.
And then by the Hambach theorem, this can be extended to the linear function on the whole space.
Yeah.
Okay.
It's all unique.
Yeah.
So let me probably, to make sure that we are all on the same ground, let me briefly sketch the main ideas for how to use the Hambach theorem. So, sketch. Functional P, which is just the mixture of xn and we define it in all element. Then, of course, if x is in C, so convergent, then P of x is nothing but the limit.
Yes.
Then we define omega on C to be just a limit. Then we clearly have that omega of x is less than P of x, well, with equality, in fact, on C. Then by Hambach theorem, we extend omega to L infinity, preserving inequality.
Yes.
And now for every x in L infinity. And the functional omega initially defined on converging sequences, when I extend it, I use exactly the same letter. So it's, might be a little bit confusing, but the extended functional is also, I use the same letter. Well, so that's the sketch of the proof. So what do we have? So this functional is linear, and by definition it coincides with the limit when the limit exists. So this
Yes.
matches the definition, so this omega is exactly the one we claimed. Let me also state a couple of properties which we have from this definition. Properties. I call that one the simple property, and these are just properties, although these are simpler than that. The first one, we clearly have that if the sequence consists of ones, so it's identical one, then the value of every extended limit is 1. It's convergent to 1, so we clearly have. The second is, the second property is, since omega of x is less than lim sup of xn, it follows that if we now take omega of minus x, then well, we also have this inequality. And if we now take this minus to write it in front of the lim sup, we will get minus lim in of xn. And using the linearity of omega, we obtain that omega of x is greater than or equal to lim in. We have that the values of omega, the values of every extended limit are between lim in of the sequence and lim sup. Moreover, it can be shown, again using careful analysis of the proved by harmonic theory, it can be shown that the range of values on a particular sequence over all extended limits exactly coincide with the intervals from lim in to lim sup. Well, this instantly suggests that, or from this fact, we instantly get that there are at least a continuum of extended limit, but it also can be shown that there are two to the power of 2 to the power of n extended limits. So the cardinality of the set of extended limits is 2 to the power of 2, and also from this inequality we obtain that every extended limit is a positive function. So if x is positive, every coordinate is greater than or equal to 0, and directly from here we get that the values of omega are also known. So from this definition it follows that every extended limit is a positive and normalized functional quantity. So we have discussed some simple properties of extended limits. Let me give you one example of a special subclass of extended limits. It's again non-constructive, and these are the, well, quite famous Banach limits. So definition: a linear function B on L infinity is said to be a Banach limit if first it is positive it is normalized and it is shift invariant. So if we shift the sequence to the right by adding a zero, the value doesn't change. So it can be shown that every Banach limit is extended limit. So that's one of the examples of extended limits. Although again, it's not constructive. And since we started to talk about all these things, I will also say that there are 2 to the power of n. So exactly the same. And there are several subsets of Banach limits of the same cardinality. So it's very peculiar sets. Okay. So any questions about this so far?
Is Banach limit is extended limit Banach limit?
Not necessarily. So the set of extended limits, or rather, I will go with this fancy B for Banach limits. The set of Banach limits is a subset of extended limits, as I said, but they are not equal. So these properties. Yeah, shift invariance. Shift invariance is a fairly strong property.
So it's just a subclass of extended limits.
Yes. And in some sense, it can be thought of a small subclass because it's very far from, say, extreme points of the set. So it very roughly somewhere in the middle. So it's significantly smaller, but well, the cardinality is exactly the same. So it's exactly the same number of elements in this.
The numbers are the same.
Yeah, the number of elements are the same. But well, the number of elements in the interval 0, 1
Yes.
is exactly the same like in this whole real line. And even if you take like 0 epsilon, it's still exactly the same. Yes, so in some sense, it's a small subset of extended limits, but well, the number of elements is exactly the same. If we consider L infinity as an algebra, then this algebra has characters. So every character character omega of L infinity is an extended limit. So this can be proved. But the characters are multiplicative functions. And also multiplicative. And also multiplicative, which means that omega of xy equals to omega of x times omega of y for every x and y from L infinity. And now I will show that this property of shift invariance and the property of multiplicativity are disjoint. So let's go with it. So let's take x to be 1, 0, 1, 0, and so on, periodic sequence. Then, if we apply a shift to it, this kind of shift I will denote it by s plus, so adding a 0. Then s plus of x is 0, 1, 0, 1, and so on. So, x plus s plus of x is identically 1. I will write 1 as this fancy one. So, b of x plus s plus x is 1 by this property. And b is linear and shift invariant. B of x plus b, well, of x equals to 1, and therefore b of x equals to half for every Banach limit. On the other hand, x times s plus of x equals to 0.
Yes.
And so, omega of x equals to 0 for every character. So we conclude that, well, I already said that B is the subset of rather, let's do like this, of extended limits. Let me go with this shout. It's not standard notation at all, but for the purpose of this explanation, they are also extended limits, but Banach limits and the characters do not use. Like this example, so it's sufficient to consider just one sequence. They take different values. Yeah. Okay. Let me go with one more example of extended limits, and then I think, yeah. And then we will go to the other subsection. Definition. A linear function, or rather, an extended limit, an extended limit, omega, is said to be dilation invariant if if we repeat every single element of the sequence twice, so x1, x1, x2, x2. So we kind of dilate our sequence. And if the value doesn't change, then we call it dilation interval. There is a nice way, nice and not very difficult, rather simple way to create or to construct dilation invariant extended limits. So, well, let's go into example. Consider an operator n from L infinity to L infinity and define it as n of x n equals to, at the bottom it will be k from 1 to n, 1 on k, and in the numerator we will have xk on k. Then, for every extended limit, since I already started to use this notation, I will use it for simplicity. The functional gamma combined with n, or composed with n, is dilation invariant. One more section. So the first one was extended limits, and we need them for the construction of Dixmier traces. The second one will be Lorentz ideal, and they will serve as a domain of Dixmier traces. B of H. The algebra of all bounded operators in the Hilbert space. In Hilbert space, well, separable. By lambda, I denote the sequence of eigenvalues. The eigenvalue sequence. Of compact operator, or compact bounded operator. And I will also need the sequence of singular values. And mu n of A be the sequence of singular values. That is mu n of A is nothing but the eigenvalues of the absolute value. Any questions so far? Okay. Now we're getting closer to defining the Lorentz ID. Let's consider a function phi on the semi-axis, positive. We also want it to be concave. And such that the value at 0 plus, so when it tends to 0, is 0, and the value at infinity is infinity. Or rather, not the value, when at infinity, when it tends to infinity, when the argument tends to infinity. For such functions phi, we define the Lorentz ideals. And phi to be a subset of all bounded contact operators such that the supremum 1/5 of n, okay, from 1 to n, mu k a is constant. So it consists of all operators such that the partial sums of the eigenvalues diverges as fast as the function phi. There is a very special choice of the function phi. So if phi of n is logarithm of 1 plus n, in this case the ideal m phi has a special notation. Is denoted in one. And this is the ideal which is probably the most used ideal in the noncommutative. For this ideal M1 infinity, we have this inclusion. So that the trace class L1 is inside this ideal, and this ideal itself is contained in every LP, noncommutative LP Shannon spaces, for every P greater than 1. So this is the trace class. And these are the Shannon ideals. Every Banach limit, or rather, every Banach limit. For every Banach limit, we have that b with s minus equals to b. So it's s minus invariant, where s minus of x1, x2, x3 equals to x2, x3, and so on. So it's a left shift. So I will leave this claim not proved so far, and then I will show you that S minus invariants imply that Banach limits are extended limits. And during these proof, I hope that I will figure out how to prove this one. So proposition. Every, or rather, yeah. That limit is a subset of its numbers. That's how it's done. Likely, every B is S minus U. That's the third thing. Although it should be second. The second thing, from 1 and 2 in the definition of non-bank limits. We have first point, xn less than or equal to supremum of xn for every n. That's what we do. Since bank limits are positive, then b of x less than or equal to b of supremum, let's say.
You mean that's a sequence, right?
This one?
The supreme of xn is the
Well,
constant
it's,
sequence,
yeah,
right?
I can go with this.
Time identity, yeah.
Yeah.
Mhm.
To make it.
Yes.
Also, bank limits are linear functions. So this supremum is a number, so
Yeah,
we can
you
factor
found,
it out.
yes. Mhm.
Which is nothing but supremum.
Yes. Mhm.
So that's what we have. But having S minus invariance, we're having that b of x equals to b of S minus of x, or rather S minus of S minus to the power of k. We can
Yeah,
apply
yeah,
it several
yeah.
times. But this sequence now starts with the kth term.
Yes.
So it will be supremum of xn for all n greater than or equal to k.
Yes.
And this holds for every k in n.
Mhm.
Therefore, bank limit is less than or equal to lim sup of xn. So it's less than supremum, but it does not depend on first finite remaining coordinates. So we can remove any number, finite number of the first coordinates, and the result does not change. And well, this one shows that it's extended limit. Now let's go with the plane. So let's consider b s minus of x. By the property 3, this one,
Yes.
we can write it as b of s plus s minus of x.
Yes, yes.
Because by property 3 it's s plus invariant.
Yes, yes.
But s plus s minus of x1, x2, x3 is nothing but, so first we shift it and then add 0.
Yes, yes.
So we want to show that this is b of x.
Mhm.
So we want to show minus of x minus x equals to 0. That will be our s minus interval.
Yeah, yeah.
But s plus s minus x is nothing but x1 and then all zeros.
Yes, yes.
And now we need to show that every okay.
This is almost the zero sequence.
Yes, it's almost zero sequence, but this claim is before this proposition. We do not know yet that Banach limits are extended limits. So we cannot say that this is zero.
Yes.
But the trick will be that, let me call this sequence y. For every n, we consider this sequence as plus of y to the power of k. K goes from 0 to n for every n. So this sequence is y, so this one, plus s0 of y, so x1 is in the second coordinate, plus s plus squared, so x1 is in the third coordinate. So what we have here is, or not even like this, not even like this. Let's directly apply a Banach limit here. Since Banach limit is a linear functional, then we have
Yes.
since it's s plus invariant, so here linearity, here s plus invariance,
Yeah.
so we can remove all of that, which is n times u of y,
Plus one.
n plus 1.
Yes.
So what I'm about to say that the norm of this sequence is exactly x1.
Okay.
And Banach limit is less than supremum. So this expression is less than 1. But here we have n plus 1. So that's what I will show now. Now the only way for b of y is to be 0. Since b of from 0 to n s plus k y less than supremum of supremum over I greater than or equal to 1, and this is nothing but x1. Or we better go, x1 can be negative, so let's go with absolute values.
Okay.
Then we have that for every n in n, absolute value of x1 is equal to n plus 1 dy. Therefore, by should we yeah, it's like this. Yeah, it's inequality here. Yeah, I almost confused myself because of this inequality. We have an inequality here. So this one is less than the absolute value of x1. So
Yes.
that's what we have. Therefore, Banach limit is less than or equal to absolute value of x1 on n plus 1 for every n. So the only way for b of y is to be 0. well, when n is large, this number, or when n tends to infinity, this number tends to 0. Yeah, and yeah, we have to say that it's more negative because y is 1. So, Banach limit on this sequence is 0, and so Banach limit is S minus invariant as well.
Yeah.
So in fact, a bounded linear functional on L infinity is S plus invariant if and only if it is S minus invariant. So this term. Because, well, we proved so far that if it's S plus, then it's S minus invariant. But the other way is simple because S plus and then S minus is identical. So
Yes,
the other way is simple.
Yeah.
Yeah, since we already proved it, let's state it. Proposition. Let omega be a bounded linear function on L infinity. Then omega is S plus invariant if and only if omega is gamma. If and only if it's S minus. So third, finally, Dixmier traces. I will follow here the paper by Dixmier from 1966. So we will deal with the Lorentz ideals M phi, and besides these two conditions, or rather three conditions, we will need one more additional condition on the function. So, theorem. If phi additionally satisfied this property, limit of phi over 2t, phi of t equal to 1. More generally speaking, it means that, or rather just a fancy word for this, this means that the function phi is of slow variation. Slowly varying. Then, for every dilation invariant extended limit omega on L infinity, the functional and here is where the Dixmier traces come in. So we define this functional as omega of 1 on phi on n for positive operators. So since we are on the Lorentz ideal, this sequence is bounded by definition, but it's not necessarily convergent. So we cannot use the usual limit, but we can use the extended limit. And if this extended limit is dilation invariant, this functional is positively homogeneous, and additive on where it's defined, so on the positive term of n bar, so the positive term of n bar. But since it's positively homogeneous and additive on the positive term, we can extend it by linearity to the positive. This is the original theorem of Dixmier, and now, first of all, the positive homogeneity here is straightforward from the properties of the single values. So if A is like constant times A, then by the properties of single values we just factor it out. So positive homogeneity is straightforward. We will prove additivity, which is tough. Or well, at least was tough. So we need to prove additivity. Well, the standard way to prove additivity is to prove two inequalities and then claim that we have additivity. So the first one is an easy part. So there is a classical estimate on the partial sums of singular values. I think it's attributed to Rayleigh's estimate. So it tells us that yeah, first of all, I didn't try Rayleigh correctly. It tells us that for every positive compact operators, we have that the partial sum of singular values of this sum is majorized by the partial sums of singular values of singular operators. And it folds for every n. So now if we divide this through by phi n, then we will get nothing but Dixmier trace of A plus B less than or equal to, I already call it the Dixmier trace, although we have not proved the linearity and we have not shown that it's a trace. But again, so this construction trace omega is traditionally called the Dixmier trace, and so I'm calling it because because I got used to do that, although we have not proved yet that it's a trace. Well, that was the easy part. The tough part is the opposite inequality. So here for gravity, we denote for a positive operator on outside, we denote by A m of A is this sequence. So the sequence of interest. First, consider a n plus 1 minus a n of a. What do we have? Just copy. Let's simplify it. There are quite a lot of similar terms in that sense. So we have 1/5 of n plus 1 minus 1/5 of n multiplied by this sum plus one more term from this sum. n plus 1a and over here I will factor out this term. Let's see what we have now. So this term is down. Since A is from the Lorentz series. For this term, mu, since the operator A is compact, mu itself goes to 0, phi goes to infinity, so all this expression
Goes to 0.
yeah, goes to 0. What about this one?
It's almost the same if n goes to the 0.
Yeah, it goes to 0 because of this extra property of the function.
Sorry,
Yeah.
also 0.
Yeah, it's also 0. So we conclude that all this expression comes to 0. As n equals to 5. Okay, so that's another observation. Well, another one which follows from this one. Now, if we take a sequence, A1
You
of A,
mean it's a Cauchy sequence?
say again?
It's a Cauchy sequence actually.
No, it would be Cauchy sequence if you have n plus k here.
But for n plus 1 it's 2. How about n plus k?
No.
Yeah, because you have
Because
more than
if you show that this is a Cauchy sequence, then it is convergent.
Yes, yes, yes.
But this is this expression, so not for every operators from Lorentz
Yeah,
series.
yeah, 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 yeah.
So now if we consider this sequence, A1, A2, A3, A4, and so on. Using this result, we can subtract. So I will replace every odd element by even element. So it's A2A, A2A, A4A of A, A4 of A, and so on. But because of this result, this difference goes to 0.
Yeah.
It's not a good idea to write it like this because we don't have ends here. So this difference
Belongs
of
to C0.
yeah, it belongs to C0. That's that. It belongs to C0. Okay. Next. Trace omega of A, by definition, equals to omega of A of A.
Yeah.
So simply by definition, nothing else. But since omega is extended limit, we can write this. Since omega is extended limit, we can write it as omega of A2 of A, A2 of A, A4 of A, A4 of A, and so on. So every element is repeated twice.
It's because it's a dilation in...
No, this is because it's extended limit. So what I've done, I replaced this sequence, which is this one, by this sequence, which is this one. So this side is C0, every extended limit vanish from C0, that's why we have it. But now, we will use the dilation and variance. So since omega is dilation and variance, it equals to omega of A2 of A, A4 of A, and to what? I will write A6 of A as well, and so on. So, we can write it as omega of the sequence which is A2K.
Yes.
That's how we can write it. And then we will need another inequality on the singular values. This is due to Hirsch. Paper in 1961. So for, again, positive compact operators, we have, so that will be inequality another way around. So K from 1 to n, UKA plus UKB is estimated by the single values of the sum. But well, of course it cannot be from K from 1 to n, because otherwise we will get equality. It's from 1 to 2n. That's the okay. So using this estimation for trace omega, or rather this equality for trace omega, we have that. Oh no, we go with this one first. Hence, using this one, trace omega of A, well, trace omega of B less than or equal to omega of 1/5n
Yes.
and this one. Almost done, but here we have 2n, here we have n. Let's get what we want. If it would be 2n, then it's okay. Let's get what we want. So omega of 2n and here we have 5 of 2n over 5n. Now this one is convergent to 1. So,
Convergent sequence.
Yep, by the simple property
Yeah.
which we discussed at the very beginning, we factor this out, the limit equals to 1, so we just get reversed.
Yes. But you probably miss the, well, you need to use the omega is defined on sequence, right?
Yeah, so that's the use of notation. So in
Yes.
fact, everywhere here, I should write sequence like
Yeah,
this.
yeah, yeah,
I
yeah,
should
yeah.
write it like this. So that's the use of notation to save the time and my nerves, because I'm getting so tired of this when
Yeah,
you
yeah.
write it in every single line. Yeah.
Yeah, it's clear. I just
Yeah.
reminded
Yeah.
them.
Yeah. Yeah. Or we can write, for instance, like this, n to this one. So it's like like a sequence,
yeah,
like
yeah.
a function. So what we have now is omega of 2n, 2n, but omega is dilation in zero. So this is nothing but trace omega of 3 plus 3.
Yes.
So we kind of use this step, but using it backwards. So here we only have even terms of the sequence.
Yes.
Second, fourth, and so on. We going back to
The trace of A.
yeah,
Yeah, it's correct.
yeah,
I have one question here.
yeah.
So, is that number, I mean, TR omega A, the functional defined in that way, right?
Yeah.
So, is that, it's a constant, right?
This one.
Yeah.
No, it should be as you said.
Yeah, after the omega,
Yeah.
after the omega, it should be a constant, right?
Over here.
I mean, omega of this is just a constant, right? So,
No, it isn't.
no, height of the sequence.
Yeah.
And finally, you go to a
Ah,
constant.
okay. You
Yeah.
mean yes.
Yes,
For every
yes.
single omega, it's a number.
Yeah, I
But
want
this
to
number
ask.
derives.
I want to ask you if this number depends on phi or not.
The phi is fixed.
Yeah, phi is fixed.
Yeah. So as
So for different phi, this number should be different.
yes. So it might be a good idea to write trace
Phi
phi
omega.
omega, because when we do this, both phi and omega are fixed.
And the one special example is you take phi equals to the rod of 1 plus 2,
Yeah.
because that function is slowly varying
Yeah.
function.
Yeah. Yeah.
Mhm.
So it does satisfy this.
Yes, yes. Okay. So such trace. Okay.
We have not yet proved that it's a
Yeah,
trace,
yeah, yeah.
but we
So-
will do it.
Such functional
Yeah.
depends on phi and also omega, right?
Omega of A2 plus I trace omega of A3 minus I trace omega of A3. And next time I suggest, next time we discuss the property of this functional. So far we only know that it can be extended to a linear functional on the whole ID. Next meeting we will discuss, we will show that it's a vector trace. This is simple. We will show that it's non-trivial and it's non-linear.